All right, one more example on using the first derivative test. And this will be example number 3. I know I have the letter C here, so why don't we go ahead and correct that? So this will be a 3. And so we'll go through the process. We're going to state the domain. So this is only undefined at x equals 0. So our domain is all reals except for 0. All right, and then determine any local extrema. Okay, so using the first derivative test, all right, I need the critical value. So I'm going to take the first derivative using the quotient rule. So the derivative of the numerator and subtract 1 from the power, that would be negative 1/3. And then times the derivative of the inside, which is 1, minus, nope, I forgot. So I take the derivative of the numerator and multiply by the denominator, right? So low d high. So I don't want to forget my low. So times x. Throw that in. Derivative of the numerator times the denominator. Minus, all right, the numerator times the derivative of the denominator, which is 1. And then that's all divided by the denominator squared, so x squared. All right, so this, I know that this will be an improper fraction, and so I can fix that by multiplying by this value. Well, let me write it out. I think we did this before in another video, but I want to kind of make sure it's clear. And then multiplying by x, so this is 2x, and then minus x minus 2 to the 2/3. And then we're dividing by x squared. Okay, so complex fraction, so I multiply by the common denominator, which happens to be 3 times the quantity x minus 2 to the 1/3. So 3x minus 2 to the 1/3. And then same thing in the denominator, 3 times x minus 2 to the 1/3. Now in the numerator, I'm going to have to distribute. So we're multiplying this term times the first term, and then we multiply it times the second term. All right, so how does that work out? All right, so because we're multiplying the first term and the denominator is common, right? That's just going to cancel out the denominator. So the whole denominator is reduced and we're left with just 2x. So 3 times x minus 2 to the 1/3 divided by 3 times x minus 2 to the 1/3, that's just 1. So we just have a factor of 1. And so we just have 2x minus. Okay, now this quantity times the second term, well, the 3 will be there. And then x minus 2 is a like base. When you multiply like bases, you add the exponents. So that's the base x minus 2. And then 2/3 and 1/3, we add that, we get 3/3 or 1, right? So just a 1. And then all over x squared times 3 times that quantity, or 3x squared x minus 2 to the 1/3. And then I just want to simplify that, distribute this, so that's 3x right there. So 2x minus 3x is negative x. And then minus and a negative 2, distribute that negative, we get plus 2. All over 3x squared x minus 2 to the 1/3. Oops, I just realized it. I distributed the negative. I forgot to distribute the 3. So that's negative 3 times negative 2, right? I have to multiply. I'm distributing. So I forgot this is going to be, let me fix that. Something was amiss. All right, so that's negative 3 times negative 2. So that's going to be plus 6. There we go. All right, so first thing, critical values. So we have G prime, or excuse me, H prime equals 0. Well, that's the numerator value. So that's when X is going to be equal to 6. And H prime is undefined. That's the zeros of the denominator. So that's when X is equal to 0 and X is equal to 2. Okay, so I have, now, remember that the first derivative test is determine all critical values that are in the domain. So because 0 is not in the domain, it can't be an extrema. But I do have possible extrema at 6 and 2. All right, so I'm going to go ahead and do the number line test using these critical values, but I know that X equals 0 is not in the domain. So I'm going to indicate that when I do my number line test. Okay, so there's my number line. All right, and I put those 3 numbers, so that would be okay, so 0, 2, and 6. And then I'm testing F prime. Let me kind of block this off, so my work there. So F prime, and we pick some values. So how about -1, 1, 3. I always pick the smaller number, the smallest integer I can find, and 7. So I actually have 1, 2, 3, 4 intervals to test. All right, and so I want to know what's happening with F prime at each of those test values. So F prime of -1. All right, so again, I'm just really looking at the sign. So if I can do this pretty easily, I will. I'm going to try and evaluate, is it positive or negative, and leave it at that. So if I put negative, so remembering that this is my H prime of X, I'm using this simplified form. Okay, and we're gonna, oh, so that means, let me rewrite this. This is H, not F. Consistency. So this is H. So I'm doing H prime at -1. So -1 here, that's the negative of -1, which is +1 plus 6. So the numerator is positive. And then -1, I'm squaring it, so that's positive. So positive times, and then -1 here, -1 minus 2, that's -3, but I'm cube rooting a negative. That will be a negative. Okay, so this is going to be less than 0. Negative. All right, and then H prime at 1. All right, again, that's going to be -1 plus 6. That's positive. And then 3 times 1 squared, that's positive. And then 1 minus 2, oh, that's negative as well. So this will be less than 0. Oh, and on my number line, I did want to remember X equals 0 is undefined. So sometimes what I do is I put a U there, just to remember it's undefined there. It's actually a vertical asymptote for the graph. So sometimes I draw a vertical asymptote, something to remind myself it can't be an extrema, right? It has to be a defined point to be a extrema. All right, so H prime of 3. All right, 3 goes in. Again, I'm getting -3 plus 6. That's positive in the numerator, so always positive. So this is 3 times 3 squared. That's positive. And then finally, 3 minus 2. Oh, that's positive. Oh, okay. So everything is positive. So this will be positive at 3. And then one more to test, H prime of 6. Let me move this function up, this graph up a little bit. All right, so H prime of 6. Oh, not testing 6. I'm testing 7, which is to the right of 6. All right, so that would be, so 7 negative, oh, here we go. So if I put 7 in there, I get -7 plus 6. That's a negative in the numerator. And then 7 squared, oh, that's going to be positive. So that term is always positive. And 7 minus 2, the cube root of that will be positive. So this will be less than 0. And so I have decreasing here. All right, so we're just, even though I could talk about increasing and decreasing intervals, I'm looking for extrema. So could 0 be an extrema? No, that's a vertical asymptote, which we can see here in this graph. We have vertical asymptote. And notice that h, the function, so this is the graph of h of x. H is decreasing on the left side of 0, the negative. And then it's decreasing between 0 and 1, so decreasing. And then it changes to increasing. So you can see that when we get that change, we have a relative, what is that? So decreasing to increasing, that would be a relative minimum. Whoops. So H has a relative minimum or local minimum. You can use either word. Relative min at x equals 2 because h prime changes. Okay, so just remember there's a reason for that, and it's one that you can memorize or understand. I always like to understand it better than more than I like to memorize. So local mins occur when f prime changes from negative to positive. But I really just think about the meaning of that, right? So let me move that back up. So why is that a min? So if h prime is negative, that means h is decreasing, and then it's positive. H prime is positive, so h is increasing. So it goes from decreasing to increasing. I've got a relative min. So sometimes I draw arrows. Whoops. Sometimes I draw. Let me make a little. So if I take my function and I draw it, it's decreasing and then it's increasing. So I think, oh, that's a relative min. Okay. So h prime changes from, and we can literally just write the signs from negative to positive. All right, so that's right here on the graph. All right, there is another relative extrema. I have h prime changing from positive to negative. So recall what that means. That means we have a function that's rising and then it's falling. So what does that mean? We have to have a relative max occur. So h has a relative or local maximum from, at what point? At x equals 6. So at that critical value, at x equals 6, because h prime changes from, need an R in there. So to be a relative max, it has to rise, then fall. Positive slopes, then negative slopes. So it has to change from positive to negative. Okay, so this answers the question. And you would not have gotten that from the graph without really studying it closely. Most students would say, oh yeah, for sure, look at that. There's a relative min right there. That's easy. But you might have missed the 6, because notice it looks like it's kind of just slowly increasing. At x equals 6, turns out that that's a maximum, because at some point this graph starts, it's not ever really noticeable, but it just gradually falls. So that actually is it's a high point, a local maximum, but it's very difficult to see. You can kind of see the increasing on this side, but it's hard to see the decreasing. So there is our analytical process for finding relative extrema.